Okay, so this chapter on air-sea interaction is basically coming to an end. This is the last topic. Maybe I'll show some more animations after this is done. But this is about sea ice formation. Again, a process that is very closely linked to air-sea interactions, right? So you can see this nice figure here, and there are some boulders on land and some glaciers sticking out, etc. But on the ocean, you have these sea ice pieces that look like leaves of a lotus plant, or what are called pancake ice. It looks like pancakes, right? Pancake is very popular in US, so we don't talk much about pancakes, but you can think of it as dosa or utapa, right? Excuse me. So sea ice formation basically happens when ocean is able to lose its heat content. If ocean is in a liquid form, that means it is warm enough to be not frozen. So air-sea interactions, cold atmosphere and winds can remove heat from the ocean and start to create the process of forming sea ice, where first needle-like frozen crystals form. They begin to hit each other and begin to form slush, and slowly the slush begins to protect further heat loss from the ocean, because it's a good insulator. Like the igloos live under ice because ice is actually a good insulator, and they begin to accrete and form what are called pancake ice. Okay, these the ice pancake ice can further coalesce or accrete to form what are called ice flows. And then they begin to have pressure at the edges, and then they get pushed up and begin to build up. You can see one bigger chunk of accreted ice flow here, right? These are the processes. But thermodynamically speaking, you have to remember something. So that's what determines the rate of formation of ice. So we know that salt reduces the freezing temperature, but if you have fresher water, it can freeze more easily. And the rate of formation also depends on temperature. So calm waters allow easier formation of sea ice, because the stormy weather in winter, as I said before, can mix up the water and make it harder for freezing to start. The other thing that happens goes back to what we learned before. When ice formation happens, it begins to push out all the gases and salts that are in it. It's called brine rejection. What happens if you're forming ice at the surface and it's rejecting salts into the ocean? The density of the water below the ice is going to get heavier, so that is going to sink, which is going to bring new water because of mass continuity. If you pull out water, you have to replace it with new water. So you end up creating these circulations, which can bring more heat from the new region, or it can bring colder water. So it can either favor the continuation of sea ice, or it can make it harder. But sea ice formation can begin to insulate the ocean from losing heat directly to the atmosphere. In other words, this process is quite complicated. The other thing that happens on the ocean is, of course, icebergs flowing in from land glaciers. What is the difference between a glacier and ice? We haven't explicitly mentioned it, but maybe some of you already know. On land, when you have snowfall, and if it's cold enough and doesn't melt in the summer, or the snowfall rate is so high that it's going on all year long, very unlikely, but nonetheless, more ice forms on top of ice that has not melted. Ice is frozen water still, so it's pretty heavy. So slowly it begins to compress the snow that's below it, right? This compression begins to form ice, which is what we call iceberg. Iceberg is very different than ice, right? Ice squeezes out stuff and it doesn't flow. It's very rigid. If you hit it, it's going to break, right? Sorry. Whereas iceberg is like molasses, it flows. So you can see the picture here. There is a glacier on a slope. This glacier flows like molasses and flows onto the ocean and forms what is called shelf ice. So as the tides and other processes are moving the shelf ice, it can break off, right? That's basically a iceberg. That's how icebergs tend to get formed. And you can see there is an iceberg floating here. The other thing to remember is that ice has lower density than water, so it floats. And most of the time, only about 10% of the glacier is visible above the surface. 90% of the glacier mass is below the surface. Okay, so you can go online and find some beautiful iceberg photos. Because of the purity of the water, they also tend to have a different, very shiny blue color because they scatter light like pure water, unlike salty water. And so you get very nice cobalt colors also from glaciers, right? So remember the Titanic. It saw icebergs and it realized that a large part of the iceberg is below the surface, so if you hit it, you're going to have serious damage. So these are the regions where you typically get icebergs, lots of icebergs, obviously coming from the land around Greenland and Labrador and so on, in the Baffin Bay, the Davis Strait on this side, the Shetland Faroes, Hudson Strait, and so on. And these are the principal glaciers, and these locations are shown in triangles, and the ocean currents are shown with these blue arrows. So ocean currents can obviously carry these glaciers down into lower latitudes, and this shows the farthest southern latitude where glacier made it in 1912, which obviously Titanic didn't know about it. They were steaming along trying to show how fast this great ship can go, as you've probably seen the movie, which is exaggerated for good effect. Nonetheless, it did hit icebergs and got seriously damaged and sank eventually. But you can see that these ocean currents, which are strong on the coastal regions, can bring these icebergs quite far south into the North Atlantic, and they are obviously navigation hazards. Antarctica is very different. We'll see later on that Arctic has got a lot of snow and ice on land that melts and puts a lot of fresh water, makes it like a lake almost, allows the sea ice to get quite thick, whereas Antarctica is surrounded by Southern Ocean, so it behaves very differently, but it has several kilometer thick icebergs, glaciers on land. So glacier can grow very thick because you can keep on dumping more snow, whereas sea ice cannot get very thick because of these circulations that get set up that I talked about, and the fact that the ice begins to insulate the ocean when it grows from the heat loss to the atmosphere. So Antarctica nonetheless has these glaciers that flow onto the ocean and form massive ice shelf ice, and there have been many examples off of Ross Sea and Weddell Sea and so on where massive chunks of icebergs have calved off. Calving is the term that's used, and they float away and melt. There are also ideas of taking such icebergs into South America as sources of fresh water and so on, because the salt content in icebergs is very low compared to sea water. And the last bit of information related to air-sea interactions is these wind powers. Ocean has constantly blowing winds, which is integrated by the ocean. So if you have windmills offshore, which is very common these days, you can produce plenty of wind energy. How to transport it onto land is a problem, plus damage by the ocean tides and waves is another problem. Plus, with global warming, if you build a nice wind farm off of Chennai by investing $1 billion or 70 lakh crore rupees or something like this, and the wind dies because of global warming and monsoon changes in 10 years or 20 years, then what are you going to do? So you have to think carefully how you build these things. Maybe they can be floating and can be moved if the wind changes and so on and so forth. But nonetheless, we can make maps of where the wind energy is very strong. Southern Ocean, because it's a channel, and it gets much colder because of the glaciers on Antarctica, has very strong winds, but it's very seasonal, right? In the southern hemisphere winter during June and August, you get very strong winds here, and surprisingly the southwesterly jet over the Arabian Sea during our monsoon season is also a very strong wind energy region. And as the seasons change and we have winter in the northern hemisphere, the northern latitudes of the Pacific and the Labrador Sea and Atlantic around Greenland and so on are also very strong wind energy locations. So wind energy is intermittent because wind is not blowing constantly throughout the day, but it can also have very strong seasonality, right? Winters typically have strong winds. Why? You can go back to your equator to pole temperature gradient and energy transport. During winter, the equator to pole temperature gradient is very strong, so you are moving a lot more energy and you are creating a lot more stormy weather because of this energy being moved seasonally. So again, see how you have to connect all the concepts. Don't just learn them and forget them. Try to remember them and try to apply them in every situation where appropriate, especially multiple concepts to create knowledge. This is why what I said before. Each concept separately is like information, but you have to combine all these information pieces to create knowledge and then create new understanding. That's very